Hello. In this video, we are going to continue our study of applications of integration. Specifically, we are going to study a little bit of simple physics, and even more specifically, we're going to study some kinematics, or in other words, the study of motion. We are going to use our knowledge of derivatives and antiderivatives to discuss the relationship between an object's position, velocity, and acceleration over time, and we will apply all of those ideas to a specific example of a ball flying up and down through the air, being acted upon by the force of gravity on Earth. So let's suppose I have an object moving around, and just to keep things simple for now so that we only deal with functions with one input variable, let's assume I have an object moving along a one-dimensional straight line path to the left and to the right. When we do that example later with a ball flying through the air, that's going to be up and down instead of left and right. That distinction is not so important. What matters is that it's one dimension. We're going to use S, V, and A to refer to three different functions: the position of the object over time, the velocity of the object, and the acceleration of the object. So all three of these functions are signed. They can be positive or zero or negative. And the reason for that is because we have the object moving along a one-dimensional track. So just like a typical number line where zeros in the middle, positive numbers on the right, and negative numbers are on the left, this means that we can interpret, for example, a positive velocity as meaning motion to the right. And we can interpret a negative velocity as meaning motion backwards to the left. Likewise, I can think of a positive acceleration as meaning my velocity is speeding up. I'm going to the right faster. Or I can interpret a negative acceleration as meaning my velocity is slowing down. So here are some things you probably talked about in even a Calculus 1 course in the past. These relationships in the left over here say that, for instance, the velocity of the object is the derivative of the position function. The velocity is the rate of change of the object's position. You've probably worked with an idea kind of like this before. If, for example, I said I traveled 100 miles and it took me 4 hours to do that, then my average speed was 25 miles per hour, 100 divided by 4. That's essentially what's going on when I see this derivative relationship. The velocity, colloquially what you could say is speed, the velocity of the object is the rate of change of its location over time. It's the distance traveled over time. Very similarly, the acceleration of the object is how quickly its velocity itself is changing. It's the rate of change of its velocity. And that's what's stated in this derivative relationship down here, which says that acceleration is the derivative of velocity. Now, another way to say that same thing is that the velocity is the antiderivative of the acceleration. This says the same idea in new language. Now, in a Calculus 1 class, you probably used this formulation in terms of a derivative, and now we have this new formulation in terms of an antiderivative. And this will be more useful in practice, as we will see in the example coming up, because an object flying through the air due to gravity, we know its acceleration because of what we know about the force of gravity on Earth, and we can use that to come up with the velocity function by taking an antiderivative. And similarly, for the velocity and position relationship, just like I have this formulation over here that you probably used in a Calculus 1 course about derivatives, we now have this other way of saying it using antiderivatives. The position is the antiderivative of the velocity function. So a couple more terms that are useful when studying kinematics. These will not necessarily appear in the example we're about to do with the ball flying through the air, but I wanted to share them now so that you can use them in some practice problems that you will work on. The displacement of an object over an interval of time is its overall net change in position. It's the location of the object at the end of time at time B minus the location of the object at the beginning of time at time A. And because of what we know about the fundamental theorem of calculus, that subtraction is exactly the same as what I would get by evaluating this definite integral here. We saw on the previous slide that position is the antiderivative of velocity, and therefore, to evaluate this definite integral, I would end up taking that antiderivative, the s of t function, plugging in the lower and upper limits of a and b, and that's exactly what I would get here. So let's look ahead down here at my little simple example that I've cooked up. Let's say I have a marble, just to give us something concrete to think about, and it starts at position 0, and over the first 20 seconds, let's say, it rolls 10 meters to the right, and then it travels 16 meters back to the left. So let's say it goes out to the right, and then it turns around, it comes backwards to the left. Well, the displacement is its change in location, and you can see by subtracting those two, this amounts to the marble ending up 6 meters behind where it started. It's 6 meters to the left. That's why that displacement is negative. Now, contrast that with the distance traveled by the object. It is 10 plus 16. It tracks the total amount of travel that the marble went through, and that's the 26. It's the total amount, the 10 plus the 16, and that's what that means. One way to think about this is the displacement is kind of like the GPS on your phone. It tells you where you are, but it doesn't tell you necessarily how far you traveled to get there. The distance traveled is kind of like the odometer on your car. It tracks how far you've traveled, but it doesn't tell you where you started or where you are now or how different they are. In terms of integration, that distance traveled by the object is given by this definite integral, dealing with the absolute value of the velocity instead of the velocity function itself. Using that absolute value means that all velocity will be counted, all motion will be counted as positive. And just like we have this distinction between displacement and distance, there's a similar notion, similar distinction between velocity and speed. Now, I know those two terms tend to get used synonymously, interchangeably in colloquial language, but they're not quite the same in this study of kinematics. Velocity is signed, it's allowed to be positive or 0 or negative, whereas speed is always going to be 0 or positive. It's the absolute value of the velocity. Let's look at that specific example that I mentioned earlier. Let's say I'm standing on the surface of the Earth, and I throw a baseball vertically, straight up into the air. And let's say I know I am somehow able to measure the exact height of the ball when it leaves my hand, the height above the ground when I release the ball. And let's say I have some device that allows me to measure the exact speed or velocity of the ball when I release it at that moment in time. Can I use that information to figure out how high the ball will fly up into the air, its peak height? Well, it turns out, yes, as long as I know a little bit of calculus and one more experimental fact about the strength of gravity on Earth that I'm going to outline now. I'm going to suggest that we use meters and seconds for the units of position and time, respectively, in this example. So, for example, I will then use the v of x function to represent the velocity of the ball, so in the units of meters per second. And we're going to use the input x as time in seconds. And more specifically, that x is measured in seconds after releasing the ball, after I throw it. Now, here's the fact that I need to know outside of that information that I'm measuring about me throwing the ball. The other fact that I need to know is that the acceleration due to the gravitational pull of the Earth, turns out that's actually constant. And it's something that can be measured experimentally. And for the sake of our example here, just to keep the numbers a little bit nicer, we're going to use 10 meters per second, or meters per second squared. We're going to use that as the acceleration of the ball as it flies through the air due to the gravitational pull of the Earth. Now, it's actually around 9.8 or so, but I'm just going to round it to 10 for the context of this example to keep the numbers a little nicer. In practice, you might just use the constant lowercase g and then leave your answers all in terms of that value and plug in a specific number later. Just to keep it easier for us, I'm going to use 10. Now, those units may seem strange, of meters per second, or meters per second squared, but remember that acceleration is the rate of change of velocity. So what this is saying is that if I throw the ball in the air or I drop it from a height, then its velocity will be increasing downwards. It'll be falling down faster at a rate of 10 meters per second every second. So in other words, if I just stand at the top of the building and I let go of the ball, right at that moment it's not traveling with any velocity. I've just let go. It has velocity 0. But after 1 second of falling through the air, it will then be traveling 10 meters per second downwards. And then after 2 seconds of falling downwards through the air, it'll be traveling at 20 meters per second downwards. That's a way to interpret this meters per second per second. It's a rate of change of velocity. And velocity itself is already given in meters per second. Now, to go back to our specific example, let's say I am measuring the exact height of the ball when I release it as 2 meters. I'm just going to pick a specific number to give us something to work with, and that's also just a little bit taller than I am. It's around 6.5 feet. And then let's say that the exact velocity, the speed of the ball when I release it, let's say I'm also able to measure that using some sort of tracking device, and I've measured it to be 16 meters per second. And it's upwards, which means that it's positive. And turns out that's around 35 miles per hour. Not great if you're a major league pitcher, but if I'm just kind of casually throwing the ball up into the air, that's about what I'd expect. Now, because of what we know from earlier about the acceleration due to gravity, that's what's telling me this acceleration function is a constant of 10. And really specifically, it's negative 10 because that pole is acting downwards, to contrast that with the velocity where I'm throwing it upwards. So let's take all of this information that I have so far and use it to figure out the velocity function. Here's what we know from this problem and from the earlier statements about facts in kinematics. The acceleration is a constant negative 10. The velocity is the antiderivative of acceleration. So it's the antiderivative of negative 10 dx. So it's going to be negative 10x plus c plus some arbitrary constant that we'll need to figure out. That comes from the fact that I'm doing an antiderivative here. And now is when I have to use the given information, which said that at the beginning, the velocity at time 0 was 16. So as it turns out, what that's going to do is that's going to cause that plus c, that constant, to actually be exactly that number, 16. But I want to emphasize what we're doing so that if you're working on a slightly different problem where that value might not end up being exactly that constant, you can still solve your problem. What I'm doing here is I'm going to plug in t equals 0. And by that, I really meant x equals 0. That's the variable that we're using. I'm going to plug in x equals 0, and I'm going to set that equal to 16, because that's the output of the function. So when I see this up here, I'm going to say, let's make x equals 0, and set that equal to 16. And as it turns out, that product is just 0, so this is another way of telling me that this c is exactly 16. But like I said, in some other problem, maybe you're given not the velocity at time 0, but the velocity after 1 second. Like there's a device set to measure it sometime later. So you just be careful about what values you're plugging in and what you're setting things equal to. But this overall now tells me that the velocity function is this. Let's use that on the next slide to come up with the position function. Here I've written the stuff that we now know so far. We have the velocity function, that's what we just found on the previous slide. We were given way back when that the height of the ball when I throw it into the air is 2 meters. That's what s of 0 represents. And we talked about on the first slide how the position is the antiderivative of velocity. So now I can just start combining all of this information. I'm going to take an antiderivative here. Antiderivative of x is x squared over 2. That's where this negative 5x squared is coming from. And as usual, I have an indefinite integral, so I have some plus c that I have to figure out. And this is where I'm going to plug in the known information to help me discover what this is going to be. In this specific example, it's going to end up being c equals 2, but it won't necessarily always be that way, so I just want to emphasize what I'm doing. I'm going to plug in t equals 0, and I'm going to set that all equal to s equals 2 from the output, and we'll see what we get. In this case, plugging in 0 for x equal to 0. Both of these terms are going to disappear, and all of that is going to tell me that c itself has to be exactly 2. And now I know that the position function is this. Now that I have that, I can explore the graph of that function, and maybe that will help us recognize or realize some things about the motion of this ball as it flies through the air. So one thing that I want to emphasize first as I'm looking at this graph is that this is not the view of the trajectory of the ball. This is a plot of height versus time. If I were to draw the actual trajectory of the ball as it flies through the air, it would look like this. Because I started at some height in my hand, I threw it up directly into the air and it fell right back down, and therefore it would just be a vertical line. But that isn't particularly helpful, so that's why we're looking at this graph where it looks like it's kind of like the trajectory of a ball as it would fly through the air, but I haven't thrown it to the right at all, I've just thrown it directly upwards. So this is a plot of time, which is x on the x-axis, and the height or position, s of x, on the vertical axis. Now we see 3 points indicated here. The one over here, the y-intercept, I could say, that's the initial height. That is me releasing the ball into the air, and that's going to be 0, 2, because at time 0, I release the ball from a height of 2 meters. This point up at the top is the peak. That's the maximum height that the ball reaches. I would like to figure out what that is. What's that height right there? And I would like to figure out when that happens. What is that moment in time where that peak occurs? We're going to do that on the next slide. But I just want to note right now from the graph that it's clearly the vertex of some parabola. And this third point over here, that intercept, that is when the ball hits the ground or returns to the ground. The reason for that is because that point has a y-coordinate of 0, so it's going to be something, 0, and we can figure out what that something is going to be. That will tell me the amount of time in seconds that it takes to get there. Now I added a link to Desmos here, so you can pause the video and visit that URL. I'm going to jump over there right now on my tablet. And you can see those points indicated with their coordinates. We're going to do some work on the next couple of slides to figure out what those values are. But you can also open up the list of functions and things to see some notes from me. And you can turn on and off the plot of the velocity function, for example. Or you could change the initial velocity. Notice how I picked 16 here because that was the value I picked for our example. You can see how changing that number changes the shape of the graph. They're all parabola, they're all quadratic functions graphed, but this is the specific one that we're working with here. And you could even scroll down and change S0, the height at the beginning of time. And you can even look ahead to see how I'm going to calculate the values of when the ball hits the ground and where it reaches the peak height. You can look back and forth from this graph in Desmos to the work on the slides in the video here that we're going through. So how can I find the peak height? Now, you may have noticed already that the position function, the height function s, is a quadratic, and specifically it's a quadratic with a negative first leading coefficient, which tells me that its graph is one of these downwards curving parabolas. So you might recognize that, in fact, when I'm saying find the peak height, this is another way of asking us to find the vertex of that parabola. And you may have memorized something about how to do that from algebra class, but I want to relate what we're doing right here to our study of kinematics and calculus and say, you know what? What's a better way to think about the peak height of the ball as it flies through the air? Look back to the graph of the position function and notice that when it reaches that peak height, its tangent line has a 0 slope. What is the slope of the tangent line of a graph? It's the value of the derivative of the function. So even another way of asking this question and thinking about it is saying, I know that the velocity is the derivative of this height, this position function, and since the peak of that function occurs when it has a tangent line with slope 0, that's another way of saying, when is the velocity 0? And that should make sense. If you throw a ball up into the air, when it reaches its peak height, when it travels up and then it hovers right in the air for just a fraction of a moment and then it falls back down, right at that moment, it has 0 velocity. It's not moving for that instantaneous moment. So when I ask this question, when is the peak height happening in time, that's another way of asking what value of x makes the velocity equal to 0. So in fact, this is exactly the same answer you would get if you apply whatever fact you've learned or memorized from algebra. Finding when the velocity is equal to 0 turns out to be the same as negative b over 2a from that quadratic function. And in this case, it's 8 over 5, or 1.6. And that's in seconds. So in other words, the peak height of the ball's trajectory occurs at 1.6 seconds after release, after me throwing the ball. And so the actual height at that moment is going to be what I get by plugging in 1.6 in for x in the s function. And by plugging in and crunching some numbers, I find that that output of the function is 14.8. That's in units of meters. That is the maximum, the peak height that the ball reaches at that moment in time. And if I jump over to the Desmos graph, you can see that those are the two coordinates on that vertex point of the parabola that we see there, 1.6 seconds, 14.8 meters. The next thing we're about to do is find the coordinates of that third point down on the bottom right there that says 3.32, 0. Let's see how to find that 3.32 value. What does that even represent? This is the time that it takes for the ball to return to the ground. Here's the strategy. Here's what we're going to do. I'm going to recognize that ground is height 0, so I'm going to set the output of the position, the height function, to be 0 itself, and we're going to solve for x, the input, which is the amount of time that it's going to take for the ball to reach that height of 0, that ground level. Now here, what I've written out is applying the quadratic formula to this quadratic equation that we have to face here, where the right side is 0. So I'm applying the formula there, crunching some numbers, and I'm going to get two possible results. And we are going to accept this value here as the number that we're looking for. And, well, you know what? It's not like that the other number is totally incorrect or doesn't have an interpretation. If I jump back over to the graph, that value is, in fact, the leftmost x-intercept there. One way to think about that is how far back in time I would have had to throw the ball to follow the same path if I had thrown the ball from ground level instead of from the 2-meter height that I have chosen in this problem. So it's not like it doesn't have a meaning, it's just not what we're looking for right now. We're looking for that 3.32. So that tells us that after 3.32 seconds, that's when the ball hits the ground. And this allows me to write my conclusion, which is after 3.32 approximately seconds, the ball returns to the ground level. And then, even more specifically, I can say that the ball is traveling at a speed right at that moment of this. Now, where did I get this information from? I looked back at the velocity function that we found a couple of slides ago. I plugged in 3.32. What you'll find is a negative velocity, which makes sense because the ball is going to be flying downwards towards the ground, which is down, so I have a negative velocity. So I can say that it has a speed of positive that number, which is 17.2 meters per second.